Hey, this is Nate here, and this is a tutorial I've been wanting to do for a while because it's so important to game programming. That is vectors and how they're used for movement in game programming. I'm going to show just some of the basic math for vectors and terminology, how to normalize them and create a movement system out of those. And I also have a demo project here that's going to come with the video. There'll be a link in the description for like the project and the repository so you can look at it and play around with it. And it showcases this movement system I've created and how it can be used in multiple different types of games without really having to do more than just different function calls within the movement system. So it's really versatile. Like here's an example. I have a little spaceship that can float with a thruster. It hits these bombs and knocks it around. There's these constant vectors. You can see it pulls it up. He goes a little slower and he goes faster. Then this right here is like it's, I guess, sort of like a black hole. It would pull you in. You can pull out of there. Here's another version where it's exact same movement system I just showed, but instead I have like no gravity and a very, very low friction on the actual impulse vector. So you can see they bounce around when they hit these bombs. So he goes much faster. And you can see the thrusters cancel each other out. Kind of cool. Here's just the basic movement, and this is a steering vector. I can thrust, go faster, slower. I believe, yeah, he gets stuck with regular boom, but I can boost out of it. What else is there? It'll do platformers, so I have a little platformer set up, and a lot of times having to do any extra for like top down versus a platformer. This will handle both. It's just, again, simple function calls for adding impulses and movements to the character. And I don't have a wall slide animation, so I just used the ground one and I flipped it, but it works. So we got him, and it'll show how to do his. He has actually a concurrent state machine, which is kind of useful to learn, but that'll be later in the video. There's also this tank. It's the exact same movement system as those spaceships and the Ninja, except this time I'm using them in a slightly different way on how I'm steering. And it's got turret rotation. I can shoot at stuff. I can blow up these bombs. It's kind of cool because the turret actually has to track where the mouse is. The mouse is the actual arrow, and then the cursor catches up with it. And even just a top down, I didn't set up shooting for him, but the only special thing here is his back pedal speed scales when you go away from the mouse. So if you're going straight at it, you go full speed. If you go back, it scales back to about 50%, and it lerps between those. So anyway, those are all the movement systems I could think of to show with this, but it's not an exhaustive list. You could probably do many other types of movement just with this basic setup that I'm going to teach here. So what is a vector? Well, when you first open a trigonometry book, the example they like to give most of the time that I've seen is they'll have a guy here, and he's got to get to the store. And to give him directions to the store, you give him a direction like this, go that way, and that is a vector. It is just a direction. The way we could describe that here is we could say, well, he's got to go northeast by a certain amount, so northeast by, like, let's just say 1 kilometer. And that would be how we describe the vector that he would go through to get there. Another way we could also describe it is go east by X amount and go north by Y amount, and which is a little more familiar here as far as how we're doing game programming. So we got an X and a Y, and that's also a vector. The first one, when we have northeast by 1 kilometer, that's called polar coordinates. And usually, we're not going to use northeast. We're going to use an angle measurement here, so that's theta. And then this distance is r, and that's always written as r theta, like that. And so these are both used at different times. It kind of depends on how much information you have at the current moment. Within GameMaker, these things are actually already built in the built-in movement system. So the polar coordinates, what we have is you have the built-in speed variable, and you have the built-in direction variable. That is polar coordinates of like the current movement vector of your character if you're using the built-in movement system. And then you also have the X and Y those are called rectangular coordinates. That has built-in h speed and built-in v speed. So those are rectangular here, and then these are polar here. And in GameMaker, it automatically does it where if you change any of these values, it'll reflect on the other. So you don't have to do the conversions yourself. There's also some functions that go along with them, like motion add, motion set. I think there's some others too, like move to points and stuff. And those will modify some values for you and do things automatically. Once we get into the code, we won't be using these specifically, but these are good to know that this is built in already. If you're not trying to do anything complicated, they're already there. You have polar and rectangular coordinates at your disposal, already ready to go. So often we want to add vectors together because we'll have multiple vectors like a movement, an impulse, maybe the wind's blowing on you or something like that. Or you're standing in water, it pushes a character. So the way vectors are added together is like if we have one vector here, and then we have another, let's just say it's like this. To add them together visually, you just take one and you place them end to end. Oops, don't need that one. And this new vector right here would be what they are added together. So this third one I drew, that would be the addition of those two. So that would be the new vector. So let's say one of these was movement, and one of these was like the wind pushing your character. When you add them together, you would have this, and that's how you simply just add them together. And you can do as many as you want, and there you go. You have a new vector just by adding them all together. So there's also some important terms to learn. They're not going to come up in code, but just the way vectors are usually written if you're looking at like some formula or some textbook or whatnot. So usually, like if we have a vector A, the arrow above it denotes that this is a vector. So that's how we would say the vector A. And let's say if it's in rectangular coordinates, we have the X and Y. The magnitude or the length of the vector is written like this. So that's just saying the length of this XY is found, and the way to find it is the Pythagorean theorem. It's x squared plus y squared. That'll give you the magnitude. If you're working with a z coordinate, it would be just plus z. It works just fine. That'll give you the magnitude of a 3D vector. And then there's also, you'll often see this little hat above it, this little arrow. Usually they'll say it's called a hat or j hat or something like that. That's the unit vector, and it's just xy, but it has a length of 1. So if A was this, and let's say that total length is like 5 or so, the unit vector would be down here. It would be a length of 1, and this whole thing is 5. So these three terms are really important to know. To find a hat, let's write it over here. It's a pretty simple formula. You got the x and you got the y of the vector from here, and you divide it by the magnitude. So important. That's why you'll see, the square root and the Pythagorean theorem come up a lot. Just distance formula. In GameMaker, point direction works. Usually you don't have to use that because your vector doesn't come from anywhere. It's already at 0, 0, so you could just do the distance formula like that. Now, to normalize a vector when we have it in polar coordinates, so in polar coordinates, remember, it was r and theta. Let's see, still have the vector A. To normalize that, it's actually a hat's a lot easier to find, actually. The computer does it for you. It's just the cosine of theta and the sine of theta. And in game space, you want the negative sign. Because if you go back here, this y value, you don't have to take the negative because it already has a sign. It already has plus or minus. That'll stay the same. For this, you need to just flip it because, in game space, your 0, 0's here and your y is positive this way. So you got to flip that when you're doing polar coordinates. And if in GameMaker, you don't have to worry about it with the built-ins. Everything that handles flipping stuff for you. But in the code examples, a lot of this, we're going to do our own movement system, and just if you ever wonder why is sine always flip negative, that's why. And this brings up a really good way to show the relation here, because what we were doing here, we were actually just finding sine and cosine directly instead of calling the function. Because if this was our vector and we turned it into a right triangle, okay, this is our right triangle. Ooh, that's a bad 90 degrees there. And then here's theta. This is the hypotenuse, and this is the adjacent side, and this is the opposite side. So to find cosine, cosine is the adjacent over the hypotenuse, and sine is the opposite over the hypotenuse. And if you look here, that's what we did. X is, let's draw it here too. X was here, and then Y was here, and the magnitude, this here, this was the magnitude, which is equal to the hypotenuse. So all we're doing is finding sine and cosine with rectangular coordinates, and here we already have theta, so we can just plug it into the actual function and we'll have it. So that's how you normalize it. It's really useful to see the relation between the two. And what also is shown here too is it's quite easy to go between rectangular and polar coordinates, because so if you had polar coordinates up here, this one here, to go to rectangular, you would just multiply sine and cosine by r. So the same vector A as rectangular coordinates would be cosine of theta times r. That'd be the x component, and then it would be sine of theta times r. And that would take you back and forth between a rectangular and polar coordinates. So in the movement system that I've created in GameMaker, there's three main vectors that are used that create the final velocity of the object. The first one being just regular old movement. And this is going to be like your inputs, or like you move a joystick, or you click the mouse and there's a destination, or maybe the AI has a path it follows. It goes from point to point. So this is the input that the object, their ability to move, and it's going to be limited to some sort of max speed. So the object can only go it can only go 5 pixels a step on its own, but other forces can act on it, and that's why we also have what's called the impulse vector. And so the impulse vector, it's stuff like an explosion, a knockback, something moves your character that, or even when the player jumps, sometimes it's better to use the impulse for the jump, and the movement's just their left and right if it's like a platformer. So this is like big stuff like knockback or explosion, something that sends a big force to the player, and its limit is like really high, like 1,000 or something like that. It can be super high. Doesn't mean they're going to move 1,000 pixels a frame, but the vector itself can be really big, because we basically want it to drown out the movement when it's a big force, and when it's a little force, it's just going to move them a little bit. And then the third one is the constant vector. And the constant vector is like wind pushes you. Gravity could be it. Gravity could be used in either, but I like to use it as the constant vector, and then the amount of gravity you kind of would adjust as the character falls and they're not on the ground or something. But it's a constant force, or like water pushes the character, so that's what the constant's for. And then these are added up, and they end up making the total velocity of the object. And the total velocity is see, we clamp to terminal velocity. So terminal velocity. And that way, the terminal velocity is going to be higher than your actual movement speed. And that's kind of the reason for even breaking these apart in the first place. Because if you weren't doing such a thing, you could go back to using these built-in ones and it wouldn't matter. But we want to be able to clamp the final movement to terminal velocity so that they can't move through walls and go crazy speeds and stuff. But then we also want the character to be able to contribute to the final movement, and that's why they have their own max speed. And you wouldn't be able to pull the max speed out of their movement and differentiate it between like the impulse and the constant. It just wouldn't work, or it'd be really difficult and it'd be pointless to try to use the built-in variable. So this is the main reason why you would not use the built-in movement variables that I keep going back to here: speed, direction, h speed. Often I see in people's code that you have like little variables like HP or something like this, and those could be useful, but then I see them basically being used exactly the same. Like they're not doing anything different. They're just using a different poorly named variable to replace these, and then they're doing the exact same kind of movement. So there's no advantage to using these two variables if you're just doing the exact same thing you could do with the built-in. But in this system, we're going to be doing something that you simply can't do with the built-in, at least not in an easy way. So anyway, onto the code. So here I have the project open, and there's a few things already set up. The collisions are set up because I'm inheriting from like a class that already does collisions for me. I'm using the entity from my basic platformer tutorial, but any collision system would work. All we care about here is movement, so I'm not going to explain how the collisions work. All you need to know is we're finding a movement value, and then we're passing it off to our collisions so that they take care of the collisions and the actual, like, moving the object itself. So all we care about really here for this code example object is the create event and the step event. So in the create event, here's the movement vector I talked about, an impulse vector, and a constant vector. For the movement vector, I want to keep track of the normal. That's going to come in handy. Then they have actual movement values. So the move speed, this is what we're actually moving, or the magnitude of that vector. The max is what we're going to limit it to. Depending on the size of your game and assets like pixel art, 15 would probably be pretty high. You would move through walls basically. So use something smaller. And acceleration, deceleration, kind of again depends on the size of your game. And if you didn't want those, you could either skip those or set acceleration equal to max or something like that. You instantly go max speed. It's all how you want to do it. Then the impulse vector has an x and y, and we're doing a cheap calculation for returning it back to 0, because once something's hit by an impulse, that impulse dies down back to 0. If you would want to maybe make bigger objects and smaller objects react differently, you'd want to add like a mass. And a simple way to do that is you take the area, the height and width multiplied of an object, and that would give you like an area value that would kind of be able to weigh, kind of a fake way to do mass. And I think Box 2D actually does that. The built-in physics for game makers, they'd use the area, but then they scale it based on like some unit amount. Say like your unit amount is 32 by 32 equals 1 unit. Like a sprite, you would divide that into whatever yours is. And so if your sprite is 32 by 32, your mass is 1. If your sprite is 64 by 64, well, dividing a 32 block into that will give you 4, because 4 32s can fit in. So that's how you find a mass value. And you can get like, a complicated way of doing impulse friction by that. But for our purposes, we're just going to multiply by this, not overcomplicate it. Constant force just has an x and y, and then the velocity right here, this is just the total speed after all those are added up in the step event. So in the step event, I'm doing 2 movements at once, optional. You can do keyboard inputs or click with the mouse. The mouse takes priority. If you don't push the mouse, it's going to check these. We get a vector towards the mouse by subtracting where we're at from where we want to go. So anytime you have 2 XYs, the one you want to go towards should be first, and you subtract where you're at from it. That's going to give us a vector to the mouse. And then these are just your standard WADs input, up, left, down, right, stuff like that. If either of these produce something that's not 0, we're going to go ahead and apply acceleration. And that starts here by finding the magnitude, which is the square root, as I showed in OneNote, where x squared plus y squared. That's going to give us the distance, or the magnitude. And we're going to divide the x and y, which is, we're going to normalize it, so we're going to get that unit vector by dividing by x and y, which is also the same as finding sine and cosine. Then we're going to take that normal x and y, multiply it by the acceleration value that we've given the character or the player, and we're going to add it to the current movement. Then we want to limit that current movement to whatever the max is. So again, we have to find the distance of what it's now at, and we're going to do the minimum of move speed max or the distance. So if this distance is less than move speed max, cool, move speed's going to just stay whatever it is here because we added acceleration to it. If it goes above it, we're just going to use move speed max as the new magnitude and never go above that by using the minimum. And if this distance here, if we didn't go above, or if it doesn't equal 0, sorry, we're going to go ahead and divide it by, we're going to normalize it again and find the move normal x and y. And the reason you need to check it's not 0 here is because if you divide by 0, your game's going to crash. You can't divide by 0. The computer doesn't like that. So it's good to check there. Up here, you don't have to check it because we already saw if one of these is not 0, which is this code block would never happen, then we don't have to worry about right here this ever being 0 because we're already preventing it here. Then deceleration, we just take move speed and we subtract the deceleration from it right here. But we want to use the max of 0 because if we don't want to have negative speed, so we're just taking the max subtracted with this deceleration. And then we do the final update, which is we found the normal here. We found the actual correct move speed based on our clamping it and keeping it below the max. So we multiply it by the normal, and that gives us our proper MoveX accumulated move speed. Then we add up all those with Vx and Vy. And by the way, I did just declare them up here because we're going to use them. I'll show later how you get the impulse and constant force, what actually adds to them. But for now, we just add up those 3 vectors, and then we keep those vectors clamped or below terminal velocity. So the minimum, either terminal velocity or distance. In this case, I have terminal velocity set at like 25. It depends on how big your game is. If you have smaller assets, 25 would probably be too high. Your object could go through a wall. Or if you need it to go that fast, you have to set up basically, you have to check in steps. When your collision system has to check in steps. So that's up to your collision system, not your movement system. So we normalize it again, and if it's not 0, if it's 0, cool. We already have, that means these are all 0. So we don't have to do this right here. We're normalizing it again, multiplying it by the total velocity that's clamped to terminal. And now here's where it's actually calling that from the entity class with the current added up velocity. So here, this is where we're decoupling our code. We're keeping things all separate. Our collisions are separate from our movement, and it keeps it really nice and easy to manage. It also makes it so, okay, you've started a new project, you can now use this movement system, but hey, your new game, maybe you want tile maps or something instead of object collision. Well, right here, you would just make a tile map collision system and plug in these values, and it would work just fine. So it's a good way to decouple your code. This is why we do it this way. And then this video, I don't have to go for like collisions or anything like that. So that does the actual movement. Everything's done there. And now we need to take that impulse vector and reduce it back down to 0. And here, if you did do a mass thing like I mentioned earlier, this is where you would do a different calculation. But for simplicity's sake, I'm just multiplying by that friction value, which was 0.85. The higher that number goes, like if it was 0.99, it would feel like there's almost no friction, and you could push it around. Like that's how you do like a space 0G type game. In the very beginning of the video where I had that that thruster spaceship that could go up, down, left, right, that one had like a really low friction value. If you want something to stop really quick as far as impulses go, you would set that value like 0.5. They'd stop in like 2 steps. It'd be really quick. So. And there's no reason to do like normalizing or anything special here to reduce it. Instead, we just check if they aren't more than 1, we just set them to 0. And constant, that just goes back to 0 every time. So when you apply gravity, let's say gravity typically downward in the game is the angle 270. You would apply gravity and a value like whatever your gravity is. Let's say it's 8. That's applied, and anytime you want to turn off gravity, you just don't apply it because this is always going to go back to 0. So now how do these get values? So the character itself doesn't, I guess they could add an impulse to themselves, but what we do is we create functions that are attached to the object or character. And let's start with the constant one's really simple. We're going to supply it polar coordinates. So we have a direction and an R or a power. So these are polar coordinates. And like I showed in the one-note example, we take the sine and cosine of this direction, multiply it by the power, and just to know, this is the same as doing like linkdir. Linkdir uses these are people usually use a lot. I use these all the time too. It just really depends on what information I have at hand and what I want to do. It just depends. So this is basically doing the exact same thing as linkdir. And these are real simple. You're just adding this power to constant. There's no cap on the constant force. We don't really have to worry about that because, again, we're going to be capped at terminal velocity anyway. And typically these are smaller values like winds pushing you and gravity, something like that. And then the impulse is a little more involved because the impulse is accumulated but also normalized just like we would with the movement. But the big difference is it has this maximum impulse force, which is like this one's set to like 1,000, which sounds a little high, but because the friction reduces it at a certain rate, a linear rate, 0.85 is what I had. This big value is just there so that like if you want to hit something with an explosion and you want it to look like it really got knocked back far, you would apply like 200 force to it. And then on the first frame it's going to fly really far. The second frame it's going to be less and less, and it's going to look really believable in like a really game sense, I guess. So this one is supplying a rectangular coordinate and a power, so it's doing the same. We're getting a vector from the position wherever this force originated, subtracting it from our current xy. That's going to give us a vector pointing towards our object. Then we're going to find the squared distance. Notice I do the square root down here. I don't do it up here. And that's because there's no reason to waste a square root operation if the squared distance is 0. And the other place I had to do it because I needed that information anyway, or it didn't really matter. But here we can skip the square root just by checking if the squared distance is not 0. And if it's not, we do the square root, and then we normalize here, and we add it to the current impulse vector. So the current x and y here divided by the magnitude, that's normalizing it, times the magnitude or the power that whatever was supplied here. And then we're going to want to limit it to the maximum. In this case I have 1,000, and if the distance is greater than that, we normalize it right here. And if not, that means we never went above the maximum, so we can just immediately set impulse equal to this Vx and Vy. We can skip normalizing it again, and that's going to give us our impulse values. Real simple. It's gonna accumulate, and it's gonna do friction right here. It's gonna bring it back to 0. And the way these are, you could call this in the step event here with, like, say you push the space bar for a jump button or something like that. But what I have set up here, like this bomb object, when it comes in contact with a character, and by the way, this code example here, it inherits from character, which inherits from an entity. So that's why I'm able to just do a collision with this parent object here. There's no reason to do like multiple collision objects with multiple different objects. It's just I just use the parent object, makes it really useful. And this image speed here is just the animation for when the bomb explodes. So if the bomb hasn't been touched yet, that means this image speed is going to be at 0, because in the crate I set image speed equals 0. Okay, it got hit, image speed goes to 1, and I move it up a depth just so the animation's on top. This is because I don't have a particle system set up to make a nice explosion or something, but it's just an easy way to do it just for this, demonstrations. And then here's what's so great about having a movement system like this. Now all we have to call is on the other, which is whatever character hit this object, add impulse, and here's the position of the bomb and this blast power. So on the variable definition tab, at the bottom, it has a blast power of 80, and it's going to knock the character 80 power, impulse power in that direction. And then for the constant forces, these are, let me pull up the room too. You can see how I have stuff placed. So I have these constant forces here, and you could actually edit it here and change the value. And these are just when the player comes in contact with them. Again, this has a collision event with the character. And all it has is a force power. It's a real simple object. It's just adding a constant force to the character. You could imagine this is like water or wind or something, and it's pushing the character, however you want to do it. And it's just other dot add constant force. These are, again, we created these in the create event of the object, so it's just calling these. And it's using its image angle. So however, that one's facing to the right. This one's facing down right. So if we look, the image angle is -45. So like when it hits that one, it's saying -45 and whatever force power it had set, and that's adding to the constant force, and now that's going to push that object in whatever things. And this makes it really easy too. Like say you have wind and water and gravity, they'll all just accumulate really easily by calling a single function like that. So that's a lot all at once. So let's actually finally run this program and show what it can do with this simple example. So I can push the WASD keys to move. Pretty simple. And here I can hold the left mouse, and if I run into these bombs, it adds an impulse, knocks it away. If I let go, you see it goes back to 0. These arrows are those constant forces. I can try to move away from it, and it still pushes me just a little. And I also have these little black hole objects. I didn't show the code, but when you push towards the middle, an actual black hole would, of course, you're not supposed to be able to move out of the middle, but I have it set so I can push through it. It doesn't actually go all the way to 0 on movement. But it's just the same as these arrows, but it's doing a calculation based on the vector pointing towards the player, towards the middle of this object, and it's pulling me in a non-linear amount towards the middle. So when I'm on the outside, it doesn't pull me as much, and on the inside, it pulls me a lot. So real simple to do with the constant forces there. And we could actually use the constant force here in the step event. Right here, before it does the total movement velocity, we could do like add, that was that function we made, or I showed, and it has constant force. And instead of, gravity is normally like 270 is the angle downward, but just for fun we'll do it, let's do it to the left, make gravity go to the left. And I don't want it more than my move speed, so we'll do like gravity's 12. That might be too weak. Oh, that's okay. I can kind of push towards gravity. I should probably give them a jump to the right button, but anyway, that's gravity pointing to the left. And you could rotate it however you want. Like we could get really stupid and put like gravdir equals 0, and here we could do gravdir plus equals, just add 2. This might be disorienting, but there we go. So now our gravity is going to rotate. It might look terrible. Yeah, it's not easy to control, but now we're fighting this gravity that's going in wild directions, and it's fluctuating. But anyway, that's how you could do rotating gravity. We might want to move the camera with that too. But so this project also comes with example objects here for different game types that would use this movement system, and then you could do many different game types with it. And the movement system I showed as an example, what I have here is set up in this character object, and it's got a little more added to it, which I'm going to go over real quick here, just to make it more robust and easier to do different types of things with. This character object, so basically you would inherit from this character object for whatever your game object is, your player or whatnot. And you can see they all inherit here, and these would then have the movement system, and they could just call whatever they need, and everything's nice and encapsulated and hidden away and takes care of itself. So you got move accel, decel, and I moved these to the actual variables tab, and then the functions that call all the different stuff. That way, if you wanted to swap them out by some other, you come up with a different way of doing them. These are right here. You could write a new one, and they're bound right here. So when the object is created, it's binding them to a variable, and those can be called by other things. Like when the bomb hits it, it would call this function, and this way too. This way, you're not creating duplicate functions. You're just binding, hey, this function along with the ID of this object. It just saves on memory. The things I added to this system is there's now a move speed mod and a move speed friction. So move speed mod, it's like if you want to add a speed booster or slow down, or where you're walking through mud or something, you could subtract from it. This makes it so you can modify your current move speed, its maximum basically, to change like the environment you're in. Friction is gonna change your acceleration and deceleration. So if you're on ice, you of course accelerate slower, and you decelerate slower, so it's going to affect those. So if you set it below 0, like 0.5, you're going to accelerate at half speed, you're going to decelerate at half speed. So 1 would keep it just normal. And move speed mod is reset to 1 after each frame, because there's no reason to track what you've had it set at, because it's one of those things like if your character has a debuff system and say they got hit by a snare, you don't want to have to keep track of how many debuffs you've put on a character to remove it back to 1. So it's going to be reset. So what you do is you just reapply it with whatever constant piece of logic is doing that. Then impulse also has a mod. It's the same as move speed mod, in case for some reason you want your impulses to act different for a certain reason. And then there's velocity and X. Now I have an X and Y, so those can be tracked and easier. Then the step event, it's about the same as the other. The only difference is that we use move speed friction. It's applied there, and move speed friction is also used like when you do a movement input. I changed it here too because deceleration happens in a different spot. Your move needs to always use deceleration and acceleration. That way you can move past it, because this doesn't have an else branch. It just says if you're moving, do this. If in the other example there was an else branch where we applied deceleration, in this case it's just stuck into 1 and then it's distributed with a move friction. So this is roughly the same other than that. The impulse mod goes back to 1, move speed goes back to 1, and here's where deceleration happens. And this is there's perfectly so that if you don't call a movement function, it's going to decelerate regardless, because you don't want your deceleration not to happen, and constant still goes back to 0. So this object can be inherited and give any other object a really robust movement system. It's pretty nice. Oh, and it also, I have set up, this is not part of the tutorial, but it has a hitbox implementation, and you can set the hit points of the character here, and it has object teaming too. That way a character can't like hurt itself. By default, every object is on its own team, so it uses its ID. But if you were to give it like team A and team B, you would assign them a numeric value like 0 or 1 for team A and team B, and then they wouldn't kill their own team. Unless you want friendly fire, then I guess you would just set it different. Let's see. So the actual objects that use that stuff are right here in the characters folder. The most basic one is the top-down shooter. There's nothing in its create. It just inherits from character. And what it does is it moves slower when you move away from the mouse position, and it uses that move speed mod I mentioned, where it's going to subtract either 0 when you're moving within the cone of 180 degrees towards the mouse, and it's going to scale it back to 0.3 being the max that it'll subtract. So it'll move 70% slower if you're moving exactly perfectly like away from the mouse. And then because we have this movement system set up, we just call the simple movement function. We don't have to do anything else. Collisions are handled by the entity class itself, so everything's nice and encapsulated and decoupled, and we can focus on game logic here and not all that other silly stuff. So, and you got to make sure you inherit the event, because that's where it's executing it from the character object. And let's see, the tank. Let's do the spaceships. The spaceships, they don't have a ton going on. They just have specific stuff for visually how their boosters going off and how this one faces the mouse. You can see it. This one, it basically lerps towards the mouse by using some calculations. And the thruster, and then again, I use move speed mod to use the boost. So when you're boosting, it goes by whatever boost power. Boost speed is 1.2, so you go 20% faster when you're boosting. The hover ship, it has a tilt angle is the main thing it does. So when you tilt left and right, there's this tilt power, and what it's doing for tilt power right here, add impulse direction, it's just doing that. Tilt power is really small, 0.8, it's pretty small, and it's tilting it left or right using an impulse. Now notice there's no movement. It's not actually using regular movement. It's all impulses and then a constant force of gravity pointing down, and so it's pushing it left and right with this tilt. And then the thruster 90 degrees points straight up. So all we're doing is applying impulses to an object, and then this movement system is taking care of everything else to make it feel like a really nice, believable game object. So, and then the tilt is clamped here with an inverse lerp towards the negative and positive of that angle, which makes it look like it's tilting left and right, but it can't go. It kind of stays upright, And so this 0G ship, the special thing is it sets the friction or the impulse friction really, really high, almost to 1. So what that means is it's not going to reduce the value as much. If you wanted true 0G, you'd set impulse friction to 1, and that way it would technically never go back to 0. Friction, your impulse vector would stay whatever you pushed it at with your thrusters. And the thrusters are actually, it pulls them into this array, and instead of calculating the angle over and over, I just hard coded them there because it's a lot easier, quicker. So it pulls them, the WADS buttons, and those are each a booster, and then it applies them to the thrusters up, down, left, right. And that the reason for doing that too is that way when we draw it, I can draw those thrusters, and I already have an array populated with which direction was pushed, and it looks a lot nicer. Let's see, the tank's got a lot going on, actually. The tank movement is actually really simple. It just does let's go straight to that, actually. It just has add movement direction, and it does a calculation based on which way you're pushing with your facing direction. So it's the opposite of where you're facing because it's pushing. But the main part it does is the gun barrel turns towards the mouse. You can't instantly turn with a tank gun. It has to rotate slowly depending on how fast the gun can turn. So all this here is keeping track of an aim direction with sine and cosine, and it's finding where it always keeps track of the X and Y. That way down here when you push the fire button, it knows where to create the actual bullet projectile at this here, and it gives it the I'm just cheating here and using h speed and v speed temporarily to carry over sine and cosine. That way, in the object of the bullet itself, I just set them back to 0 after using these to calculate the actual velocity of the bullet. There's no reason to make separate variables when I can just kind of bogart these just on create and then stop using them. So that's the tank. It turns towards the mouse basically, and the reason for all that too is we're drawing an arrow. The arrow points towards the mouse, and then the aim reticle is where the actual gun would shoot, like its aim as it turns. So, and then we draw the bottom of the tank and the top of the tank. This is why I've seen people make tanks with like 2 different objects. Like, why bother? Just draw it right here and you're done. You don't have to do all that between object communication or whatnot. You just draw it. It looks just fine. Let's see. The platformer is a little more complicated. Let's do it because it has. It's more like if you took my basic platformer tutorial. It's very similar. It doesn't do all the same stuff, but it does most of them. And it uses a concurrent state machine, which I don't want to go into too much because it should be another video really. But the way it handles them too, let me close them so it's not too much. There's these state free is where you would actually have your button presses in its update function. And my states are all structs. That way you can have state variables that are specific to this state. You can contain them here. And then the object itself doesn't need a bunch of crazy state variables. They're all contained in the struct. And then the struct has an update function, which is called, and then it does these button remembers to change the state. So action state change to slash or throw. Real great way of doing states is concurrent states like this. Let's look at so it has the way it handles those action states for throwing the ninjas or the kunai and swinging the weapon. It uses broadcasts in the actual animation itself. So in the broadcast event, it's going to just call the action state the broadcast function, and it's going to say what happened. So if we look at like the slash, you have attack start and attack end. That's when the hitbox is going to be created, and then that's when the hitbox is going to be deleted. So the hitbox happens from here to here, and then there's no more hitbox. And that's handled by just the broadcast message is sent to this state is slash. And if we look at the animation broadcast, it says, okay, if it's attack start, right here we're going to create the melee attack, and we're going to keep track of that hitbox. And then, okay, attack ended, and the hitbox didn't get destroyed for some weird reason. It's going to destroy it. So that's a real easy way to, instead of, you never want to, through code, you never want to say like if frame equals this or if frame is less than that. That it's really difficult. It's not difficult to do, but it's just a lot of extra code for no reason. Instead, this is going to happen only when it matters. The sprite itself is going to tell it, hey, this happened, and then you can just have a broadcast sent to this state, and the state takes care of it. Same with the animation end. When we're done swinging the sword, we want to go back to state free. So in the object itself, animation end, it's just going to call animation end on the state. So the state's going to go, oh, okay, so I can do state change. And this action state change is just a function right here at the, it's defined on the object itself. So it's basically calling its parent action state change. It's saying here's a new state, and this is a constructor. It's sending a constructor, and so it says, okay, finish the current state, call whatever function, maybe that state needs to do some kind of specific logic. So finish the current state, here's my ID, and then now action state equals this new one, and call the constructor. So that's how it does a state change, and everything's nice and encapsulated in its own like state struct. It's really great way to do it. Now the rest is almost exactly the same as my basic platformer tutorial, so I'm not going to go over it. The only difference is we use the action animation here to override the locomotion animation, because in GameMaker your animation state and your actual game logic are kind of intertwined. It's not like if you used Unreal, you have like an action slot you can stick in front of your action state or your actual animation state, and it overrides it automatically. This is just a good way to do it. I'm sure there's multiple ways, and that way we can set up concurrent states without having to have a bunch of stuff for our locomotion. Our locomotion's going to be the same regardless of what we're doing. And then in the states themselves too, like where you throw the kunai or you swing the weapon, it does apply to like when you swing the weapon, it does like a slash, or actually it does it here. It applies an impulse to the owner, and if you're in the air, it applies an impulse with a slight offset angle. So again, calling these movement functions throughout the states is just really easy. We don't have to like do any calculations. It's just like, hey, move in this direction and do this. So, all right, so let's finally run this and just look at these objects real quick. And so here's the platformer, the most complicated one probably. And he can hit these, and he's the actual hitbox itself is giving an impulse to these balls, and they actually, when they hit each other, they're just doing, hey, impulse at a vector that points away from the other one. The rest is kind of basic platformer stuff. You can spawn bombs too, just to see, like, maybe you want to make a game where you jump with explosions. You could do that. It'd be kind of fun. Those sandbags have hit points. So here's the tracking I was talking about. It follows. And you can shoot it, it turns. This is like mud, where it does that move speed mod. It slows him down. You go slower through the mud. I guess it's mud. You can bombs, knock him back. I think his speed's so slow that it can't really get out. Yeah, he can't get out of the black hole. I could blast him out. Yeah, see. This guy's the most boring, but it does have back pedal speed. And here's the tilting I was talking about. And we could actually steer him around. See, the tilting has a max, doesn't go past 25. Pretty cool. And what else? 0G guy. You can really knock it around too, because it has such low impulse friction. You can really, I'm steering it just with the bombs, which is kind of, you could probably make a game just out of that. Or you can use these in conjunction. And basic ball is boring. And here's the ship with the booster. He hits bombs, reacts somewhat realistically in a game sense, and can't get out of the black hole, but you can boost out. So that's all the objects, and that's the whole video. Hopefully it wasn't too much to take in all at once. The main takeaway really, other than just like here's a movement system and here's the code, is the beginning where I showed how to use vectors and normalize them, because you'll use them in all sorts of things. Even just like a moving menu or something, you may need your menu item to slide into place with a vector, and then maybe like an easing function, so it looks like, you ever hear them say like add juice to your game? Well, you're going to use vectors to move stuff in ways, like especially when you want to combine movement and make things look really cool. So vectors, the math itself is really the really important part, and then here's just one implementation of how to use it and how to make a really robust movement system that you can then transfer into other games without having to think how this stuff works again. You just have these simple functions. Let's pull them one more time. These functions here, where you just call these, add in movement, add impulse, etc., whatnot. And again too, there's the built-in H speed, V speed. So there's your rectangular coordinates for your built-in movement system. And if I could type direction and speed, those are your polar coordinates for your movement system. And then there's like it's motion add, and there's also motion set. Those are built in. These are all built-in functions. And I think there's some others. I bet if I click on these, go to the middle mouse, you can click, see there's motion add. That's what it does. And then there's a whole section on movement. And there's also gravity and friction too, and the direction of gravity. These are all built in. When I see like people post their code and they're like, I'm new to GameMaker and I took this tutorial, and you'll see like they're not using the built-in movement. They're using like these other variables, and there's no reason to use them because they're doing the exact same basic movement with them. So again, you could just use these instead of adding your own variables and overcomplicating things. So once you want to do impulses and constant forces and do a lot of different interactions, that's when you move into learning some things about vectors like I taught here, so you can make up your own movement system or use something similar to the one I'm providing. So anyway, thanks for watching. Hopefully I can get some more videos out like this. It's holidays right now, not a lot of time. And the project itself and the repository, there'll be a link to it in the description. And I'll also link some other videos on vectors from like other more math oriented, and they go more in depth, so you want to learn more about them, where they're actually probably going to use like more proper calculations for gravity and friction and mass and stuff. But in games, we can simplify that, so we can get away with it because we want faster code and we don't need that robust calculation. So anyway, thanks for watching.